Walter Mayr holds educational in design, manufacturing, and finance, boasting decades of executive-level professional experience in the energy sector. He specialized in conducting targeted techno-economic analysis that explore the correlation between system behaviors, flexible power supply strategies, and operational modalities. Currently, he serves as Director of International Business Development, Shuangliang International, in addition to his role as Director of SLG Europe. Sorry if my English, Walter is better. And good luck. 20 minutes, 5 minutes? Okay, thank you.
It. Okay, buenos dias, good morning. I try to be a little bit efficient. Unlocking the full potential of green hydrogen shall be a backbone of a net zero future. A future Shuangliang already practice. We have our own manufacturing facilities with net zero carbon completely organized, based with boilers for steam production, waste heat recovery, with heat upgrade, heat pumps, heat exchanger, cooling solution, whatever. Just as we have the structure, use energy right. Over the past 12 years, we also have built a comprehensive portfolio of new energy technologies, including carbon capture units, polysilicon furnaces, photovoltaic products, as wafer and solar modules. We are a group with a turnover of about $10 billion US. This leads us to the first critical part in green hydrogen production, bankability. Bankability means one of the key operation risks for realization of a green hydrogen project. As a client, you want to be sure when you order spare parts or a refurnishment of a stack that your supplier is still existent after that one. The second critical consideration goes to the supply chain. We have in Shuangliang over 80% of the equipment design manufacturing in-house, which emerges as a competitive advantage. It helps us to strike, deliver on time, and guarantees product quality, especially with the certifications required in Europe. The third critical point goes with the equipment reliability. Of course, we have long-term references, which everybody require, but it's impractical in the current phase, as green hydrogen production is still in a developing phase. A small sample, we do a lot of CFD simulations to optimize flow geometries in the channels and minimize the pressure drops to enhance the efficiency. And that is every time is a new product. So that gives us a delay if you want to have a reference for 5 years. That didn't exist. So at Shuangliang, no product change gets approved without a performance validation. Such a validation is performed in our 25 megawatt test center, a facility that ensures the technology meets the operational standards. A second large test facility is a smaller one that have 10 stacks inside and operates just only with PV of our own factory. That means we have the full fluctuation from the renewable power as basic. The setups gives us real-world renewable power fluctuation experience. It's enabled us to further improve operational flexibilities, and at the same time, we can practice to capitalize every single kW of renewable energy. In addition, we are able to reduce the cold starts to nearly zero. The past, current, future research development efforts are laser focused on 5 pillars: longevity, performance, operational stability, plant availability, and cost competitiveness. Research and development exceeds far behind the foundational electrolyzer components. Crucially also, research and development validation process is conducted in close collaboration with client representatives. This leads us to the main topic of our speech, the presentation. We want to enhance availability and performance while mitigate operational risks through life cycle modeling of green hydrogen assets. Of course, you might assume this is just another multi-physics system simulation tool, but we are based on real practice experience. And we want to understand how the customer think, which problems he faces, and this gives us the basic to improve our solutions. Especially, we want to know about the equipment behavior, every equipment behavior in an aged stage. Degradation is happening, and degradation is not just only focused for the electrolyzer stacks. Every asset in and outside the green hydrogen plant have a degradation. The optimization is always an ambition in parallel consideration of CapEx and OpEx. For every performance, we quantify the trade-offs. What operational improvements we can achieve, but at which cost. So, why prioritize life cycle modeling? Because an integrated green hydrogen system, every single operational adjustment or design modification has a cascading effect on all interconnected assets. Our analysis spans a full in-house value chain. We start with renewable energy, sourcing by power profiles given by clients. From there, every stage of the process have losses, whether in form of energy dissipation or hydrogen wastages. We are targeting a utilization rate under both beginning of life, end of life conditions. Crucially, life cycle modeling of green hydrogen systems need a precise focus. So there we start with the finance first. It's not surprising. PCU, power conversion units, and electrolyzer stacks accounts for a larger share of OpEx compared to a CapEx. OpEx for this core assessment comprise of various components: interest, depreciation, power losses, non-primary power consumption, operation maintenance, as well as infrastructure. Notably, these cost breakdowns are evaluated at the beginning of life stage. Degradation impacts then on two ways the overall cost. Indirectly drives higher energy consumptions, but indirectly also reducing the hydrogen production, the output, both of which erode project economics over time. This leads us now where we have chances to improve. We don't go each one, just a few headlines. The goal here is to drive down levelized cost of hydrogen. And just to clarify the ongoing research and development, we parallel do it on the electrochemical side also. Within every measure, we focus on two most impactful drivers: the renewable energy costs and the capacity factors. The core of this strategy lies in the maximizing the economic utilization of available energy resources through optimized operational time. Now start with the power conversion unit. Now comes the practical experience for you. An IGBT, this is the industry's most widely adopted technology for power conversion in green hydrogen systems. But like all electrochemical processes, IGBT operation generates substantial heat that must be efficiently removed, an imperative for preserving device lifespan and system efficiency. Liquid cooling emerged as the preferred thermal management solution. Liquid cooling have two levels: cooling water, chilled water. For instance, if you upgrade into chilled water, you pay a penalty of $250,000 as CapEx additional for an 80 megawatt plant. But if you get an efficiency better of 0.2%, you are equal in finance. That means the threshold of many IGBT devices can exceed far more with chilled water. That brings us to the next consideration: electrolyzer sizes. Bigger stacks are cheaper. very clearly. If you have a 10 megawatt stack, that's nur marginally as total cost bigger than 1 5 mega stacks. So, but what is often overlooked here, however, is the cascading savings across utilities and supporting infrastructure. Deploying only half the number of stacks, 110 versus 2 5 mega stacks, translate to proportional reduction in piping networks, structural supports, instrumentation, and still even spare parts. All of this influence CapEx and OpEx. A second key lies in the power density, which exhibits a direct linear correlation to the energy consumption. To address diverse project needs, Shuangliang offers a portfolio of up to 6 different stack sizes with 3 distinct power density ratings. As shown in the chart there, the large and medium stacks perform economically better based on 30 euro per megawatt hour levelized cost of hydrogen of energy, but also twice the size. Next focus, utilization dynamics. For off-grid plants, the trade-off between hydrogen production, energy utilization rate, and levelized cost of hydrogens gives you as a clear economical optimization threshold. If we want to achieve a near maximum energy capture, it requires a very high capex, makes the configuration economical and viable. Downsize to 70% of the theoretical full utilization capacity strikes the optimal economic balance. This setup results in a 12% loss or curtailment rate at the beginning of life. At the end of life, we already have 15% decline due to component degradation, efficiency losses. Any further reduction and reducing the capex of the hydrogen processing capacity pushes levelized cost of hydrogen upward. A similar story goes with the BESS. BESS, very, very common today from the price level. So an important step, integration of BESS, is the ratio between the power supply and electrolyzer capacity. This ratio is plant neutral within the same geographic area. It's just an adoption of BESS charging compared to BESS discharging capabilities, influenced only by the steps of the electrolyzer sizes. The ratio basically economical to it well for full load as well as for part load. Step 2 then is how much BESS makes sense, a decision between economics and environmental targets. What is the capacity factor? It is the difference between what you get from the PV and what you lose. That means consider losses in AC-DC conversion, losses using the BESS because you have a round-trip efficiency, and of course, power you are not possible to convert because it's not economical. So this situation leads to different capex structure where the money from the equipment goes from electrolyzer to BESS and opposite. So operation with this BESS gives you a capex value which is 20% lower and gives you an OpEx value which is about 8% lower. A 70% solution looks not so bad. You have a little bit higher levelized cost of hydrogen in beginning of life condition. As soon as you go end of life, the deficit will rise. The best sizing correlation is about 3 to 4 times the PV installation. Here in the south, slightly larger, do longer daylight hours in summer. In north of Spain, we have half an hour more time for discharging on peak days. Shuangliang have a slogan, use energy right. We already had it. So therefore, we search for heat recoveries. Where the energy goes, we put inside the electrolyzer. 17% of this renewable energy is normally extracted by cooling water out of the electrolyzer. At the 80 megawatt plant, this is staggering 137 gigawatt of thermal power. 137. And in addition, you need 7 gigawatt electricity only to operate the pumps. That's a lot of money. Any waste heat, once recovered, can be utilized. In the northern part of Europe, it goes directly into district heating. Here in the south, we don't need that one. So we can improve the energy balance in carbon capture units, or we can generate chilled water. What makes chilled water so useful? Chilled water or chilled cooling water, CCW, you have 3 places in your hydrogen unit they need it. Basically, for an 80 megawatt plant, we need about 555 cubic meter at the beginning, what is about 3.2 megawatt thermal duty for our 80 megawatt plant. The cooling load is crucial for fire cooling, gas-liquid separation, and most notably, hydrogen purification. Over the last 2 years or 3 years, when green hydrogen plants are more common, electrical chillers are utilized in hydrogen plants because they are easy to operate. But an electrical chiller has quite a big financial penalty. You pay for our standard plant about $25,000 every month only for electricity. By contrast, if you use a waste heat-driven absorption chiller, he will deliver economic performance much better. CapEx, we only use about 70%. Operation costs, we go down to 30% compared to an electrical chiller. Of course, for operation reason, you may need a small electrical chiller for startup. At the beginning, ask why we do the modeling by ourselves. We already mentioned it, to understand the needs of our clients better and creating more competitive solutions. That is why we put efforts into modeling. We recognize that public companies have available industry tools for the same purpose. We still believe our hands-on project support can accelerate identification better. Moreover, critical decisions are made mostly well before feed initiation. Evaluation is essential in all the stages, especially within pre-feed. What other sets Shuangliang apart? We are a provider of end-to-end integration energy solution. Shuangliang is committed to supporting clients with cost-competitive green hydrogen plants with proactive engagement from the earliest project stage to ensure optimal design, efficiency, and economic performance. Some additional reason why Shuangliang: we are an original equipment manufacturer with deep expertise in hydrogen production, CCUS, utility technologies, proven track records in robust, scalable energy infrastructure. We have more than 3 years real-time experience operating green hydrogen plant. Currently, we are completing the engineering for large green ammonia, green methanol plants of 600-800 megawatt, which will go to the manufacturing within the next few weeks. No difficulty, our production capacity is 5 gigawatt. In partnership with the Spain company IDEA TSG, we offer more pre-engineered standard module solutions. We optimize feed work, basic design, engineering workflows, cutting-edge timelines, and mitigate technical risks. We are familiar since over 20 years with PD, with all others, CE compliant. We know CBAM currently, so we are well satisfied and prepared for the European market. Our global footprint: we are present in 20 different countries with dedicated technical maintenance teams. Our Madrid-based European headquarters boosts our regional presence. And as we have in the speech, we prioritize operational risk mitigation from the project inquiry onwards. Technical economic insights shared today are grounded from real-world project experience. If you want to know more, you can discuss with us at booth E11 or you can contact us by email. Thank you very much.
Thank you so much, Walter.